Welcome back. Today we're going to talk about limits at infinity. Let's start with the definition. Given a function f over a specific interval a to infinity, this a is just a constant. It could be from negative infinity to positive infinity. At the moment, we only care about the fact that the function is defined over an open interval. It means going toward infinity is possible. Then we say the limit of f of x as x approaches to infinity equals to L if for large x values, the corresponding y value of the function is getting closer and closer to L. Means it doesn't really matter how large you pick the x value, the corresponding y value is getting closer and closer to a specific constant value, L. That constant could be a number, or in some cases it could be infinity. Means if you let the x value get larger, the corresponding y value is getting bigger as well. Similarly, you can define the limit at negative infinity by saying the limit f of x as x approaches to negative infinity equals to L if by choosing a small x value, small in terms of large negative numbers, then the corresponding y value is approaching to a certain number. That number again could be positive, negative, infinity, constant. And just to make sense of it, here's an example. Okay, so let's assume given the function f of x is x plus 2 divided by absolute value of x plus 1. And they ask you to figure out what is limit f of x as x approaches to infinity. If you remember, when we started to discuss the definition of limit, we would pick corresponding x and y value, and x value when we figure out the corresponding y value, and it's like a guessing game. Where does it end up if you pick these x values? So here, I'm going to start with a number like 10 for x, then I'll pick 100, and I'll pick 1,000, I'll pick maybe 10,000, and so on. A million. Doesn't really matter. So I'm letting the x values to get larger and larger. You do not need to start with 10 because 10 is not a really large number. 100 is not a large number. But I'm going to start with these numbers just to see what happens to the y value. Okay, so if we pick, let's say 100 and replace it for x into the function f, what you get is 102 divided by 101. So you'll get 102 divided by 101. Similarly, if you pick 1000, you'll get 1002 divided by 1001. You pick whatever, this is 100,000. If you pick 100,000, you'll get 100,002. One extra zero here. Divided by 100,001. What you would see is 102 divided by 101 is almost like 1.01. Let's say, I haven't calculated this exactly, but let's say it's something like that. Similarly, if you calculate 1002 divided by 1001, it would be something like 1.001. You calculate 100,000, you'll get 1.00001. Again, these numbers I'm just estimating. It would be probably close to these. So what do you expect is, if you let x values getting large, and picking positive infinity at the end, you pick a huge number at the end, what happens to the y value is the y value is getting closer and closer to 1. So I can say the limit of f of x as x approaches to positive infinity, what do we get is corresponding y value is approaching 1. So I should say it's 1. Similarly, you can try for limit f of x as x approaches to negative infinity. See what do you get in that case. I'll pick again x and y values. You don't need to pick a million of them, just maybe 2, 3 would be good enough. I'll pick negative 100, negative 1000. Again, this is not the normal way to calculate. This is just to understand what we're trying to achieve. Okay, if we pick negative 100, replace it in the function, you'll get negative 102 divided by absolute value of negative 100 plus 1 would be 99. If you replace here, I'm going to replace only two numbers, it's too many. let's try this. You'll get negative 10,002 divided by 9,990, since there is an absolute value. So what we get is something, again, this is close to negative 1.01. This one is close to negative 1.001, maybe one more zero. And so what do I get is the y value is getting in closer and closer to negative 1 if I pick the x value approaching to negative infinity. I can say the limit, I expect the limit to be negative 1. This is kind of the basic idea of what is the behavior of the function as x value is getting larger, what happens to the y value. I can say, if you think about this function, how does it behave is, I don't really know what happens in the middle, but if you pick a large x value, let's say 100,000, what you get is y value is approaching to 1. Not even 1 precisely. It would be somewhere close. It would be somewhere here. If you go further, if you pick 1 million, what happens is you get closer and closer to that y value of 1. So this is what happens is, as you get closer to the positive infinity for x value, the y value is approaching to this dashed line. And on the other side, you will have something like this, where the dashed line here is negative 1. Since the x values, as x values are going to negative infinity, y value on the graph is approaching to, this is part of the function f. This is curve as part of the function f. The curve is approaching to the y value of negative 1. Okay, so these two tables, this is what it represents. This has a meaning, and these two curves somehow get connected, or maybe there is a vertical asymptote. Something happens in the middle. We don't really care at the moment. It's just these infinity limits tells you about the behavior of the function at the infinities, not in the middle. Okay, so horizontal asymptote. What is a horizontal asymptote? Is basically these dashed lines. I should have used a different color. So here, these dashed lines. Let me change the green line. This green line, where the function is approaching to that line, is what we call it the horizontal asymptote. Okay, so the most you can have is two horizontal asymptotes. So one is at the positive infinity, the other one is negative infinity. Sometimes you do not have the horizontal asymptote, something like x squared. The function does not approach to any constant, so there is no horizontal asymptote. Sometimes you have one horizontal asymptote. On both sides, the function approach to same thing. They approach to the same dashed line. And in this example here, we have two horizontal asymptotes. One is y equal to 1, the other one is y equal to negative 1. So the basic definition of the horizontal asymptote is, we say the line y equal to L, in this case, for a last example, y equal to 1 and y equal to negative 1, is called the horizontal asymptote. So the horizontal asymptote is that dashed line for the function f if one of these two cases happens. It could be both of them, but one of it is enough. If the infinity limit at positive infinity equals to L, or the negative infinity limit equals to L. So in the last example, positive infinity limit was the positive 1, so the line y equal to 1 became the horizontal asymptote. And if we looked at the left-hand side, the function will approach to y equal to negative 1. Therefore, y equal to negative 1 was another horizontal asymptote. We had two of them. So this kind of, I drew a picture already to say that there is two horizontal asymptote that I already mentioned above. One was at negative 1, the other one at positive 1. So you would have two horizontal asymptotes, y equal to 1 and y equal to negative 1. These are the two horizontal asymptotes, the last example. you only look at the end behavior to figure out horizontal asymptote. So you calculate the two limits, limit at positive infinity and limit at negative infinity. If the other side of the equality is a constant, this L, if it's a constant, then you would have a horizontal asymptote. If it's infinity, positive or negative, then you would not have any horizontal asymptote. Okay. There is one theorem, because we don't want to use this table over and over. So this is a main theorem to calculate limits at infinity. It's very important to know that if you have limit 1 divided by x to any power, as long as that power is positive number, and x is approaching to positive infinity, then this limit equals to 0. It should kind of make sense that if you're dividing 1 by some huge number, if you replace x with infinity, infinity to any power is still going to be infinity. It means you multiply it by itself. If you take a square root of infinity, you still get an infinity. 1 divided by a large number is approaching to 0. This is only makes sense in the limit value. You cannot say 1 divided by infinity is 0. This doesn't make sense. This is not true. This is not true. It is true if there is a limit involved and you say you have x approaches to infinity. This makes sense. Because you're saying what happens at the end if we calculate this limit is that the y value is going to become 0. Okay, now let's use this idea to calculate the certain limits. Here's the first one. Calculate the following limit. Maybe I should have started with something simpler. So let's start with this one first. Let's start with limit 5x plus 1 divided by 3x squared minus x. We will generate the idea from here, then we use it in the last example as well. The limit 5x plus 1 over 3x squared minus x. And we want to calculate the limit as x approaches to negative infinity. Again, we have only one rule that we need to use, is that limit 1 divided by x to some power equals to 0 as x approaches to either positive or negative infinity. It doesn't matter which side. This is always true. I'm going to use this over and over. But if you look at this fraction, you don't see any similarities of 1 divided by x to some power. By the way, if this numerator instead of 1, if it's 2, this is still supposed to be true, because you can write this as if it was 2 divided by x to the power r, and you can say I can take the 2 out and multiply it later. The 1 divided by x to the power r is still 0. 2 times 0 is still going to be 0. So this limit here that I wrote as 1 divided by x to the power r, it could be any constant c divided by x to the power r. That limit should still be 0. This is true for any positive or negative c, as long as c is a constant value. So here, what we do is look at the fraction, figure out the biggest degree of x. You can see the denominator has degree 2, x squared. So what I'm going to do is I'm going to divide everything by the largest degree. Maybe that's the best choice of action in this case. So here you will say I'm going to divide everything 5x by x squared plus 1 divided by x squared. Here denominator 3x squared divided by x squared and minus x divided by x squared. I can do this since you do it to both numerator and denominator. X approaches to negative infinity. You can divide both numerator and denominator at the same time. Okay, simplify. What you get is limit x approaches to negative infinity. What do we have in the numerator is 5 divided by x plus 1 over x squared, 3 minus 1 over x as x approaches to negative infinity. Then now you can use this property and say, what is the limit of 5 over x as x approaches to negative infinity? This should be 0, since we already have that property. So c could be 5. What is the limit of 1 divided by x squared as x approaches to infinity? This is still 0. Since r could be 2, 1 divided by any x to any power is still 0. The other term here in the denominator, the limit of that is still 0 again. So what we have is 0 plus 0 divided by 3 minus 0. That is 0 divided by 3, simply 0. So I found that the limit of 5x plus 1 divided by 3x squared minus x is 0. That means if this was a function, f, then f would have a horizontal asymptote, at y equal to 0. This 0 tells me the horizontal asymptote. Okay, now let's look at the last example, the one that I skipped already. Okay, so here, if I look at this radical and compare the denominator and figure out what is the largest degree for x, I should say the largest degree is x squared. But it's not true, since you take a square root of x squared and the result becomes x again. So the largest degree is x. So what I'm going to do is I'm going to divide everything by x. So here I will say 3x divided by x minus 5 divided by x as x approaches to infinity. And numerator, here if you divide by x, this is correct, but I want to put it inside the square root, so I'm going to divide it by square root of x squared. That means I can combine the square roots together, and instead of dividing by x, I can divide by x squared underneath the square root. Because the square root of x squared is simply x, so I basically divided by x, not by x squared. 1 divided by x squared. But I'm going to do it underneath the square root, therefore it will be the same thing. Okay, now simplify. This is limit x approaches to infinity. Numerator is square root of 2 minus 1 over x squared divided by 3 minus 5 over x. Now I use this property that we have. Negative 1 over x squared limit would be 0. 5 over x limit would be 0. So what do you have at the end is square root of 2 divided by 3. There are shortcuts to this, but I don't want to give you a shortcut. I just want to make sure that you follow these steps so there is no mistake if you're doing shortcut. Okay, here, let's look at another example. What is the limit of square root of x squared plus 1 minus x as x approaches to infinity? One thing that I wanted to mention is if you have 0 over 0, we say in terms of limit, if you have limit x divided by x as x approaches to 0, you should, if by replacing 0, you would get 0 over 0, which is undefined. But you could simplify it first and then you say it's 1. Similarly, you should have the same tactic if you're dealing with infinity minus infinity, because the infinities may be different. This infinity may be different from the other infinity. If you replace infinity into this limit, what you get is square root of infinity squared plus 1 minus infinity. This is not, do not do this. Do not cancel out and say this is equal, cancel out with that. This is equal to 1. This is not correct. This is not true. Do not do that. So what you can do is you can think about it as you have an infinity term here, and this one gives you another infinity term, because square root of infinity is still infinity. So infinity minus infinity is kind of impossible to calculate, because you don't know which infinity is larger, which one behaves, how big it gets when you take a square root or multiply or add or something like that. So comparing these two terms is not that easy. So what you can do is you want to get rid of the square root. And how you do this is always by multiplying the conjugate. X squared plus 1 minus x. I'm going to multiply a conjugate. Square root of x squared plus 1 plus x. And whatever I multiply to the numerator, I should multiply the denominator. There is no denominator, so I put a 1 here. Square root of x squared plus 1 plus x. By the way, you can add the infinities. Infinity plus infinity is still infinity. You're adding two huge numbers, the result is a huge number. 2 infinity doesn't really make that much sense. 2 times infinity is still infinity. These infinities are not numbers. They are just representing huge numbers. Okay, so now simplify as x approaches to infinity. Equals limit x approaches to infinity. Square root of x squared plus 1 minus x times square root of x squared plus 1 plus x conjugates. I think you've multiplied these too many times already, so you would get this radical times that, this radical times the other one. These two multiply by each other, and if you simplify, you just need to do these two multiply by each other and the other two multiply by each other, since they all cancel out the other two terms. So you get square root of x squared plus 1 squared, which is simply x squared plus 1, and negative x times negative plus x is minus x squared. And denominator, square root of x squared plus 1 plus x. Now simplify. This is limit. Numerator is 1. Denominator is square root of x squared plus 1 plus x, as x approaches to infinity. Here's what you can do. Now, if you replace infinity into this fraction, what you get is 1 divided by square root of, I want to show you this as well, infinity squared plus 1 plus infinity. This is okay. It's not the correct way, it's mathematically, but just so you can skip over some steps, you don't always have to divide by x. So what you get is 1 divided by square root of infinity squared plus 1. This is an infinity, not the same infinities, but it's another infinity. It's still a huge number. If you add it to the other infinity, still a huge number. Now 1 divided by a huge number, that you can estimate as 0. In terms of limit, you can do this. But in terms of constant, this doesn't make sense that you're dividing 1 by infinity, where infinity is not really a value. It's just representing that there is a variable that is getting larger and larger in terms of limit. Okay, why didn't I do that in the earlier example? This is one thing that you should notice. In the earlier example, if I replace infinity somewhere here, what do I get is 5 times infinity, for example, plus 1. Let's ignore the negative part for the moment. You'll get 3 infinity squared minus infinity. I can answer the numerator and say the numerator is 5 times a huge number plus 1. That's still a huge number. But denominator, this subtraction, not possible. 3 times infinity squared is infinity minus infinity. You cannot say that this infinity squared is bigger than that. This is not a way to deal with it. So this is not a possible way to simplify. Even if you simplify it, even if you say, okay, this one was smaller, so I get infinity over infinity, you cannot say I'll cancel out these two and equal to 1. This is not correct. Neither this one is correct. This one is okay, but you cannot do this. This is not correct. So now if you would have done these processes, you would end up with 1, which our answer was 0. So this is, make sure that you do not do these steps. You cannot subtract infinity from each other. You cannot divide infinity from each other. You can add two infinities and write infinity. That's fine. You can multiply constant by infinity and say that's infinity as well. That's all right. Okay, so make sure that you're using these techniques that we learned. So here, another example is limit sine 1 over x as x approaches to infinity. This is just to make sure that you understand the concept of if there was no sine, and if it was only limit 1 over x as x approaches to negative infinity, what would you say is if it was only this? This should have been 0 by the property that we know. So if there is a sine operating here, what you can say is I can replace the infinity and say this is the same as sine of 1 divided by negative infinity. Since I accepted that 1 divided by infinity is 0, so this must be sine 0. And what is sine 0? It's simply 0. Again, you did not subtract any infinities from the other. You do not multiply, you do not divide infinities by each other, but you can divide a constant by infinity in terms of limit and say this is 0. 2, 200, 2 million, doesn't really matter. As long as the denominator is infinity, the numerator a constant, this is always 0. Okay, so this is possible. Okay. Here's one more example. Limit x squared plus x divided by 3 minus x. Now, we learned that you should divide by the largest term. Not always the best choice. I want to show you here. If you divide by the largest term, x squared divided by x squared plus x divided by x squared, denominator 3 over x squared minus x over x squared as x approaches to infinity. What you get is, okay, numerator is 1 plus 1 over x, denominator is 3 over x squared and minus 1 over x squared. This is not the best technique, since at the end what you get is, you say, okay, by what we learned that this limit will be 0, this part will be 0, this one will be 0. So you have limit 1 divided by 0. And your answer must be undefined at this moment, or does not exist. But this is not correct. 1 divided by 0 in terms of limit doesn't mean that it doesn't exist. It means it is possible that the result is increasing toward infinity or negative infinity, or maybe into both sides in some cases. Okay, so this is not true either. So this technique of dividing by the largest term is best if you pick the largest term from the denominator. So if you pick the largest term from the denominator, that is the best choice. So here, from this point on, if you're looking at the fractions, look at the denominator, pick the biggest term in the denominator. In this case, the biggest degree comes from x. So I'll divide everything in term, not by x squared, but by x. I'm going to change this to x. And you will see why I do this is, let me write this. X squared divided by x is x, x divided by x is 1. And what do you get here is, sorry, this should have been 3 over x squared earlier, but I forgot to write that. So here you would get 3 over x minus 1. Okay, now, you see this part is, I can say the limit of this term is 0 as x approaches to infinity. So therefore, what do I end up with is basically limit x plus 1 divided by negative 1 as x approaches to infinity, because the term 3 over x is 0 as you calculate the limit. So what is that? Let's simplify it. It is limit x divided by negative 1 plus 1 is the same as negative x minus 1 as x approaches to infinity. Now replace infinity. What you get is negative infinity minus 1. If you subtract 1 from negative infinity, this is still negative infinity. So this limit turns out to be negative infinity. It's not undefined. It turns out to be negative infinity. It means if you let the x values get larger and larger, what happens to the y value? It's getting very small. It's going toward negative infinity. Here's another type of question that may come up. If you replace infinity into the function, into this equation, into the limit, what you get is infinity cubed minus 2 infinity squared. You may ask yourself, okay, which one is bigger, these two? And you say this is bigger because it has the higher degree. Not always the case. If I put a sign here, then you cannot compare it like that. So I recommend to avoid that is, this is not correct. You cannot subtract them from each other. You cannot say infinity cubed minus 2 infinity squared equals infinity. This is not correct. Do not do this. Just replace the infinity to see what happens. It's not possible to subtract infinity, so I ignore this process. What I can do is I can look at these two terms and say, what do they have in common? They have x squared. And what is left is x minus 2 as x approaches to infinity. Now replace infinity. See what happens. You'll get infinity squared times infinity minus 2. If I ask you what is infinity minus 2, you have a huge number, subtract 2 from it. The result is still infinity. So I can say this is still an infinity. Now you can multiply infinity squared by infinity, because you're multiplying a huge number by another huge number. The result is still a large number. So this limit turns out to be infinity. The correct calculation, you should follow this procedure. You cannot simply say, okay, this term is larger, even though it makes sense that the cube is always bigger than the square. But in terms of calculation, you have to factor it. Okay, these are normally the type of questions that come up. If you're dealing with fraction, look at the denominator, pick the largest degree. If you're dealing with sine and cosine or whatever, first replace the infinity to see what happens. If you're dealing with square roots, the largest degree is not what you see underneath the square root, but it's the square root of that. So square root of x squared would be simply x. That would be the largest degree. And horizontal asymptotes are basically what you get as the limit at infinities. So in all these cases, the numbers that came up in the end was the horizontal asymptote. If you had negative infinity, for example, as the result, that means that function here, when we calculated the limit, ended up with negative infinity as the limit. So it means this function has no horizontal asymptote, since the infinity limit became negative infinity. Actually, you should consider both direction. X approaches to negative infinity as well, but it turns out to be the same thing, since the function has higher degree in the numerator than in the denominator. Okay, I think this is good enough for this section as well. Next time we'll continue on 3.5, and we're going to discuss how to use these information. We're going to build all these information to graph functions precisely. We discussed increasing and decreasing interval, concavity of the graph, local maximum and minimum. Now we're trying to build the end behavior. That means the horizontal asymptotes. We already talked about vertical asymptotes. We know the domain, and so we will put all these information together, so hopefully we can get a clear view of how the graph of any function would look like. Okay, so I'm going to stop at this point.